Okay, so this video is about conservation of energy. So we kind of started talking about today that conservation of energy really kind of falls from this idea that the mechanical energy before some action is taken has to be equal to the mechanical energy after some action, like a ball rolling down a hill or up a hill or whatever. So this is really true for things that we call isolated systems. So what does that mean? What is a system? Well, a system is just an acknowledgement of all the different objects that take part in the particular object that or scenario that we're looking for. So if we're talking about maybe this block rolling down a hill, what would be the system for that? Well, obviously you'd have the block. Let me do that in a different color. So you would have the block, you would have the ramp, and you'd also have the earth. Now, why would you have to include the earth in that particular system? Well, we know gravity is the thing that is pulling this thing down the ramp. We know that we have gravitational potential energy. So if we don't include the earth, then there's no way for us to include that gravitational potential energy. So that is our isolated system. Now, that doesn't include anything like a hand coming in and pushing on the object. That doesn't include friction, because that would be considered to be an outside force. Then that would not be considered an isolated system. So this conservation of energy, of mechanical energy, is true for isolated systems only. So let's take a look at a situation, and we've seen this situation before. Hey, look, it's our trusty physics textbook, right? And then down here is our ground. There we go. Okay, you made fun of me for that last time. Anyway, so we know that we are a certain distance y above the ground, okay? And sometime later we let this thing drop and we let it hit the ground, okay? So what if we did our energy bar charts for something like this? Well, we know that we have lots of different choices ahead of us, and this is our before look. So what kind of energy do we have before we let this thing go? Well, we know we have all of it as mechanical. There's nothing that we've been talking about outside of that, okay? And it turns out that all of it is also gravitational potential. So it's all gravitational potential, okay? Then let's take a look at the energy bar chart after we let this thing go and right before it hits the ground. So kinetic, UG, US, and ME. Again, we know it's all mechanical. Okay, so what kind of energy do we have down here at the bottom? Well, at the bottom, it's all kinetic energy. So if we have that mechanical energy before equals mechanical energy after, that would mean that the potential energy, gravitational potential energy on the before side has to equal the kinetic energy on the after side. Okay, so that's kind of the stuff, the review of the things that we did in class today. Let's take a look at this in a slightly different way. We're going to backtrack a little bit and say, okay, here's our physics textbook. And just to kind of review some things, what kind of forces are on this physics textbook? Well, right as we let it go, really the only force that we have on it is the force of gravity, and that is m times g. Okay, we can really be thorough here and say that, oh, all of our forces have to equal mass times acceleration, so therefore mg equals mass times acceleration. Okay, now I'm going to show you kind of some math trickery. I'm not expecting you to remember this, but it's a way that I can show you how to get to the equations that we will eventually be using for energy. Okay, so we have this kinematic equation that says that final velocity squared equals initial velocity squared plus 2a. And in this case, it's y, because we're y distance above the ground. Okay, I'm going to backtrack over here for a second. So we are y distance above the ground, so that is how far it's going to fall when we allow it to. Okay, I'm going to solve for acceleration here. So, and then we also know that the initial velocity was nothing because we just dropped it. So that means our acceleration is vf squared over 2y. Just doing some quick algebra. I'm going to take that acceleration, plug it in there. Okay, so we have mg equals m times vf squared over 2y. I'm going to write this in a slightly different way. I'm going to multiply y to the other side and say mgy equals 1/2 mvf squared. All right, well, take a look at this for a second. We have on one side of the equation, on this left side, we have a quantity that only deals with the initial position of this object. Okay, so it's only the initial position. Okay, it has nothing to do with the motion. It's only about where this thing is, and it has to do with gravity. All right, and if we take a look on the right-hand side, we have something that only deals with the final velocity. All right, so only dealing with its motion, not how far it went, not where it went, but only its motion, its velocity, and only on the final side. So if we backtrack to here, we see that we have this equation that says that the initial potential energy equals the final kinetic energy. We know potential energy has to do with how far away from the reference point you are. We know that kinetic energy has to do with how fast or what your motion is like. So this equation is actually showing us the exact same thing. It's saying that our potential energy, mgy, has to equal our final kinetic energy, which is 1/2 mv squared, and this is final velocity. Okay, it doesn't always have to be final velocity. It could just be initial velocity, especially if we're starting off with kinetic energy. So that means that this equation here is the equation that we have for ug. It's mass times gravity times y, the distance away from the reference point, or the height. Okay, and then our kinetic energy equation is 1/2 mv squared. Okay, let's just take a quick look at the units for what this thing would look like. And it might be easier to take a look at the potential side, but if they both have to be energy, then they both have to have the same units. So mass is measured in kilograms. The acceleration due to gravity is meters per second squared. And then y is a distance, so we add another meter to that, and so it's kilogram meters squared per second squared. That's a mouthful, so we just call that a joule, and we have the abbreviation J. So that is a unit for energy, joule. We can look at the kinetic energy side and see that it's actually the same thing. Mass is measured in kilograms. Velocity is meters per second, but that is squared. So we have a kilogram meters squared per second squared, again, which is also measured in, or also called a joule. So that's the unit that we have for energy. So what we have here is conservation of energy, that our potential energy, and we have our new equation for it, equals our kinetic energy. Okay, I'm going to leave you with a problem that we saw in class, and that was this problem right here. Okay, so a block going down the ramp. Okay, I'm going to give you some specifics here. I'm going to say that we have a 5-meter tall ramp, and the mass of this is 2 kilograms. I want to know what the initial potential energy is, and I want to know what the final kinetic energy is. And you'll answer that in the questions below. All right.